Hi, my name is Molly Ward, and I'm here with Devin Lane and Paul Cunningham to talk about our senior design project, GEthereum, which is sponsored by General Electric. The purpose of this project is to create a blockchain-based system for GE's gas turbine customers to keep an audit trail that can keep data secure from any cyber attacks or data breachings. The purpose is for the graphical user interface, which is a downloadable app, to capture whenever configurations were changed, who changed it, and what was changed. This also has access control purposes, so only authorized users can access this blockchain. This slide covers how this project is implemented within GE systems. So on the left are the gas turbines, which send information through the industrial control systems, and our project captures these configuration and log files, parses them through our Python scripts, and is put on the blockchain and read through the GUI to display whenever a configuration change and a history of when and who changed these configurations.
Some overview of our application. You can see Python is really the centerpiece of this app. So what it does is it looks for the logs and machine files, reads that data in, and then it compiles the Solidity smart contract, deploys that contract onto a chain, and then submits all of the metadata that we parse out of this file to the blockchain as well. And then Python also queries the state of the blockchain and displays that in our graphical user interface. It should be noted that all of these functions are wrapped within the UI.
The app starts with the deployment of our Solidity smart contract, which reads in the raw data contents from the machine files and the entirety when the contract is deployed. And from there, a hash of the file is generated. And when the blockchain is queried, the Python script compares the hash with the queried and the generated hash from the device file, and if those are equal, there will be no change and no configuration added to the blockchain. But if there is a change, there will be a difference between the two codes, and that difference will be sent to the blockchain to store the difference between the altered configuration and the machine file that was already being stored on chain.
This is the general methodology that we followed to make sure that GEthereum was scalable, robust, inexpensive, and safe. These include modularity of our project, minimal on-chain processing, encryption and decryption to prevent data breaching, and event-driven with focus on the customer. This slide goes over the concept of modularity, which focuses on separating functionality between files, classes, and functions. This allows for easier troubleshooting and makes our project more scalable. To give an illustration of this, we can go through the actual code structure of our project. So here you can see we have our backend modules separated by functionality. For example, this file contains all the functions for deploying a contract. This file contains all the functions to display our file differences, and this file allows us to query the chain and generate the history in the UI. These are all imported by the main application file, which is where we design and set up our UI. Another important factor to consider on this project was how monetarily and computationally expensive processing on the blockchain would be. We try to keep this at a minimum, which means that we only used the blockchain to store and retrieve our data. We used our host machine, in our case it was a laptop, with Python to do all of the other computation. For example, this is generating hashes, generating patches, and others. This keeps the cost of on-chain usage to a minimum. We wanted to make sure that all of our data was encrypted before we uploaded it to the chain. This makes it so that anybody that could decode our input to the functions wouldn't be able to see the actual metadata. It would look like a bunch of gibberish. We did this using a symmetric key, which is used to both encrypt and decrypt the data. This is an illustration of that. So you can see here, when we use this key, we can encrypt the text test The result of that is this long string that doesn't really mean anything. If we want to decrypt this and decode it, we can actually see the raw text. Part of our methodology was making sure that our application was both event and user-driven. That every time you push a button in the GUI, this triggers a back-end process to run code. Any exceptions, meaning errors in the program, don't cause the app to crash. Instead, there's a descriptive, rich logging interface that reports the issue to the user. And everything is wrapped in an intuitive, descriptive graphical interface.
The way our app actually communicates with the blockchain is through a Solidity-created smart contract, which this is just one program that contains all of our functions in order to add hashes and the metadata to the blockchain and also retrieve them in case of an audit. And so Solidity is its own language that communicates with an Ethereum virtual machine, and in our case this is Ganache. And by doing this, we scale down cost, and this goes hand in hand with off-chain processing. And this code is just data that resides to a specific address on the blockchain. And the smart contract also implements a form of access control, and this was decided to use a role-based access control, which gives certain Ethereum wallet addresses a certain role in order to only call certain functions within the smart contract, and this prevents unauthorized wallets to interact with the blockchain to retrieve the data that is being stored on the blockchain. So this is just a brief overview of our contract, which includes a library that has admin roles and user roles, and then this is the actual contract itself, which contains the functions to add new users or admins and remove them if that is needed. And this is all the data being stored on the blockchain, and these modifiers right here are placed within the functions that give only certain Ethereum wallet addresses access to calling these functions.
Some of the strengths of this project is that blockchain is tamper-proof. There's a rich user interface. The storing of patches on-chain allow for a visual history of how the file changes over time. And finally, our application is deployable and distributable. On the other hand, some of the weaknesses are that a public blockchain can be used, which would open industry ports to the internet, allowing for potential security risks. Also, the cost of including patches is much higher than just small metadata, which can increase the total cost in the end. And finally, as the history grows, the performance of our system may slow down. So now we're going to talk about our GUI. And as you can see here, this is our main window in which you can deploy a new contract to begin with this button, which scans in the configuration file. And from here, we can publish a new configuration with this button, which simulates on the back end a change in an IP address within the configuration file. And as you can see here, it shows the file diff, the hash, and the previous transaction. And you can continuously publishing new configurations, and they will each compare to the initial deployed contract. And each of these configurations just records the difference from the original deployed contract.
The unique portion of this project that we were able to implement is including a patch of the file on the chain after the initial state is uploaded. So the very first time we deploy a contract, it uploads the initial state, which includes the raw file contents. You could also call it the text of the file. After this, each time the IP addresses change, which is simulated by publishing a new configuration, a patch between the new file and the original file is generated, and that's what's stored on chain. And that is done each time we publish a new configuration. The interesting part about this is that we can generate a history of the file and see what was changed in a rich HTML format. So you can see here, this IP address changed from 106.143.203.18 to 243.100.73.132.
So like I mentioned earlier in the presentation, we have implemented parameters to prevent malicious attacks by only permitting certain addresses to access or add info to the blockchain. So when the contract was originally deployed, the account that deployed the address was deemed an admin, one of two roles within our roles library in our smart contract that has the ability to publish new configurations, query the chain, and give certain addresses different roles, either as an admin or a user's. So as you can see right here, obviously this account can publish new configurations to the blockchain. But if we were to change to a different account, so this is Ganache, and I'm going to add a different account to demonstrate that this account cannot add to the blockchain because it does not have a role. So the changes were saved, and if I were to publish a new configuration, this address does not have a role as an admin, so it cannot publish new configuration. And somewhere in this code it does say that this account does not have an admin title. So what we do is we have a user management that the original account that deployed the contract can give access to this account, an admin title that would allow him or the person with this wallet to apply changes to the blockchain. So I'm going back to the original account that deployed the contract, and as you can see, can still publish configurations. So this tab right here is user management, and for the purposes, this tab gives a username, so we'll call it test, and then we go back and we take this account that we want to make changes from, and we will give it either a user role or an admin role. But for the sake of demonstration, we'll give him an admin role, and we'll commit him, and as you can see, this account is now deemed an admin. So we go back to credentials, and we'll go and add this account in there. And so now we have switched to another account, and we are able to publish new configurations showing that only the person who is an admin or gives admin purposes is allowed to publish new configurations and query the chain.